Okay, now that we have all of the reactions, we've got the reaction at A, the shear, the vertical is going to turn out to be 5/8 of the total load. The one on the right was 3/8 of the total load. That was the one that we solved for with our method of consistent deformations. And when we worked out the number, we got the moment here at 4471. That should turn out to be WL squared over 8. It's a negative value in the sense of the frowny face we actually have here from our internal sign convention. But let's just check something real quick and see if we do get what we should. There it is, 4471.25. So that really is WL squared over 8. All right, so now look at the shear diagram. In effect here, this reaction at the left was 5/8 of WL, boom, come up, come down by WL, we end up at 3/8 WL. It's a negative value, and then the reaction closes it off. Right? Then we take that, integrate it to get to the moment diagram. Right? It's going to be a second order curve. Right? And so notice something, straight line segment, right? 3/8 WL over here. And then we got 5/8 WL. And it's really convenient. It turns out that as we track along at WL, or W that is, here for the slope, oh, that's going to put us, since this W is the slope, that's going to put us at 3/8 L to get over to this 0 on the shear, which is going to be the peak on the moment diagram. Since we have 0 moment at the far right, then this area right there, 1/2 of that times that is going to give us the peak moment happening right there at 3/8 L. Right? And then, of course, they're triangles, right? And by similar triangles, or however you want to look at it, that is the same as that is. And so if we're 3/8 L from the right to 0, then from 0 to here, we're at another 3/8 L. The reason why that's important and nice is those two areas balance each other. And so that takes us over here. We fell off to 0, and now back we fall over to 0 at the same distance. There's a symmetry there. That's really a simply supported beam with a uniform load on it, is what that actually is. And then this little trapezoidal area will have us drop down, and that'll get us to the final moment at the far left at minus WL squared over 8. And so that's a little bit different way of having created the moment diagram from the shear diagram, but it's equally valid. You can go right to left or left to right, whichever way you like to do it. All right, and then once we have the moment diagram, of course, divide by EI, and that gets you then the curvature diagram, integrate that twice, and that will give you the deflected shape. In our case, we know that the negative moment region here is going to create concave down in that same region. And so all the way up to the inflection point, we have concave down. At A, we had to have absolutely no rotation. And so, boom, that's why we put the French curve down and drew that coming down. The rest of it, though, has positive curvature, so concave up. And so we have a rotation out at the far right. And so we end up with this sagging that's happening. Notice at the inflection point that the beam has actually displaced down and it's rotated. Right? That's a part of the bending action. So the inflection point does not mean 0 displacement, it means 0 moment, not the same thing. So that's our shear moment and our deflected shape. So let's talk a little bit about what we may have learned here. We had as our initial guess for things, if we go back, we said our moment at A was approximately, we thought maybe WL squared over 12. Gee, we had it was between WL squared over 12 and 0. And we said, well, we'll take half of it, WL squared over 24. That seemed, kind of fair, right? Maybe. We'll see. Didn't work out that way. The final, or the actual moment at A, or that reaction, was equal to a WL squared over 8. That was larger than the WL squared over 12. That was kind of interesting, right? For our reaction, we had, well, from both of the two extreme cases, we said WL over 2. And knowing that we didn't have a symmetric situation, Well, it didn't turn out that way either. The real one that we ended up with was that RA equaled 3/8. Oh, not RA, equaled 5/8 WL. It went up also. So note something here and something to learn, right? It was the other reaction that was 3/8 WL, right? The stiffer elements of an indeterminate system will end up with or attract larger fraction of the load effects. So let's go back and look again what we had. We had an asymmetric support system, although we had a symmetric structure and a symmetric load. Right, and so there's your 3/8 WL at the right, 5/8 WL at the fixed end at the left, and this moment that turned out to be negative than WL squared over 8. Right, and so the effects of this thing, compared to a simply supported beam, the effects of this W got shifted over to the left. That made that reaction larger, and it also kicked up what this moment was, because it was, in this case, that fixed end is the only thing preventing that beam from rotating at the ends, because the other one is free, and that created sort of this absorption of things over here on this stiffer or more rigid end. We can use that in future estimates.